fascinating, and it's also very much a hot topic in statistics and in artificial intelligence and in machine learning and so on. And so at least I can tell you today some of the basics of what it means, which as you can find it in Solomon's book, which is full of quite a lot of misprints and I think some errors, probably no terribly serious ones, but he says some things which I just didn't have time to check, and I have some doubt about if they're true or not, because he gives the usual summary of the usual theory, which involves lots of implications and definitions and so on. And some of his definitions seem a little bit different from other people, and then it's to puzzle to work out if it's the same or different. No, and
if it makes you feel better, we don't have to put the video online. I mean,
yeah, no, you can. I can say this. I would love to say this to him and discuss with him why he makes some definitions, some ways he does, and if he realizes this or that. And I'm not really an expert in this field. I have used graphical models in forensic applications, for instance, to model mixed DNA profiles in murder cases. Well, actually, some of my students did the actual calculations. And okay, but so I've seen it in action, and when there are conferences and people talk about graphical models, I always go to their talks and so on. But I notice I'm getting a little bit out of date because new things keep happening. So graphical models are models which look like this. I don't know, so that's a graph. And there are two main families of graphical models. There are graphical models based on undirected graphs, and there are graphical models based on directed acyclic graphs, also known as tags. So I could draw the same picture and then add some arrows, and then it would be, obviously I can direct every edge in this graph such, yes. Yes, this is called the directed acyclic graph.
You still need one arrow.
Yeah, one arrow. I have.
Now it's important.
Actually, no, it doesn't matter.
It's not. Oh no, it's not.
It doesn't matter. Okay, so some terminology. So, and these are sort of completely different things, but the theory of the models of these ones use a lot of the theory of these ones for various reasons. And when studying these ones, it's often you want to kind of convert them into things like this for various reasons, which I try to explain. Okay, so a directed acyclic graph is a directed graph, which means every edge in the graph has got a direction, and there are no directed cycles. Not no cycles, but no directed cycles. So directed acyclic graph is a little bit ambiguous. Okay, and all the graphs today, and it's for Solomon, are simple. It means no multiple edges and no loops. A loop is a self-edge. So there are never loops or multiple edges. And they're either this kind or this kind. And people working in this field invent statistical models based on graphs nowadays with, I think, 4 different kinds of arrows. 4 different kinds of edges. Single arrows and double arrows and dotted lines. And make sensible models out of them. And so what has this got to do with statistics? Is that, so here we have some vertices, and we have a graph, and so it has some vertices, and it has some edges, and here's another graph which has vertices. Well, M has directed edges, and what do I want to say? Oh yeah, what these things have to do with statistics or with probability or with artificial intelligence is that each vertex is say V here, corresponds to a random variable xv, which I'm going to suppose takes values in some space, curly xv, because sometimes it's useful to name them, and they can all be different. They're all, this picture which you see here is supposed to be a model for the joint distribution of what you could call x on its own, or you could call xv is xv v in v. And similarly here too, each vertex v corresponds to a random variable, and usually the space or set in which the random variable takes its values is fixed in advance. So for instance, we say that the random variable xv takes values yes and no, or 0, 1, or 1 up to 20, or is continuous, or something fancy, some fancy space. And okay, and here too, the graph is supposed to be a model, or it's supposed to describe a set of joint probability distributions of these, random vector, if you like to call it. It's supposed to be a plain capital V. So, yeah. So basically, to each graph, to this graph, and these sets xv, we describe a family of joint probability distributions of such random variables taking values in such spaces. And we do that by saying that a number of conditional independence assumptions should hold. And these models, so I'm trying to slowly work to what you, yeah?
So just to check and understand, so
Yeah.
there's, when you look at the random variable, there's this implicit probability space omega, and the omega should be the same for every vertex, and xv is a function from omega to a curly xv.
Yes, so somewhere in the background there is a probability space omega f p, and there are all different kinds of p's possible, and all these xv's are functions from omega to the respective curly xp's, but we're not interested in the whole probability space, we're only interested in the image measure, the joint probability distribution, which that whole thing implies. For this thing, so basically the joint probability distribution of, the probability distribution of this random vector is a probability measure on product xv over v in v. Yeah. Do we usually write that? I think so. Yeah. So, okay, and you give all these things, sigma algebras, and you demand things to be measurable and so on. And I'm very comfortable, most comfortable, and one can be very comfortable when these xv's are so-called Polish spaces, complete circle geometric spaces. They can be finite, in particular finite sets with discrete topology. And the sigma algebras are the Borel sigma algebras, and so on and so forth. The thing is that if you do it in a more abstract, when we talk about conditioning in probability theory, if you do a very abstract, purely measure theoretic point of view, there are lots of technical details, and you have certainly, in particular, have to say almost everywhere or almost surely with almost every sentence that you write, which is pretty boring. And if you do it in Polish basis, you can generally trust that you don't have to bother. I mean, it still should be there, but it doesn't harm to forget it. If you see what I mean. It's not a technical issue. It is a small technical issue, but it doesn't actually spoil things. Essentially, the theorems are essentially right. Sometimes you should have almost everywhere written, almost surely somewhere. I just want to briefly say where they come from, or sort of where the roots of these things are. These models come really from mathematical physics. And interacting particle systems. Think of each vertex is a particle, and the vertices its neighbours, so this vertice's neighbours are the other particles which it interacts with directly, as a direct interaction. So like, the energy of the whole system is a function of the values of this group of whatever, of variables. And you may think of them as particles, but they could be particles of completely different natures and so on. This is a proton, and this is an electron, and this is something else completely different. And the values the variables take can be in completely different spaces. But anyway, an H means direct interaction, which leads, of course, to correlation, or more probably statistical dependence. But the interaction between these neighbours with one another also leads to statistical dependence far apart. Anyway, so it sort of comes from mathematical physics. By the way, the graphs are always finite. And people working, like Frank van Hollander, and a big history of people working on these things in mathematical physics and studying so-called Gibbs measures. They're interested in, if I tell you some specification of the interactions locally, what can you say about the global property of the XV's V and V, where this is now infinite? But we don't go into that kind of thing. But it sort of comes from mathematical physics, and this means a direct interaction. And now, directed acyclic graphs come from economics, and social sciences, and medicine and biology. And the common word which joins these things is that people are interested in causality. So here a key word could be interaction, I suppose. These are models about interactions, but these models are models about causality, and people in machine learning and artificial intelligence nowadays are busy taking, say you have a whole load of people, and each person has got values of each of these variables, and you can get data, you can get big data, a lot of people, a lot of properties of all those persons, economic, medical, whatever. And you actually want the computer to tell you, to learn from the data, what causes what. What is the cause of what? And the arrows stand for direct cause. So this vertex, the variable which is here, is in some sense, it also goes into, it's also go. To drive artificial intelligence and philosophy. and law and so on. What do you mean by causality?
Cycles in causality are forbidden.
They are forbidden,
But
yes.
It's not so clear that in true life.
Yes. Now, it is clear in true life that they are forbidden if you take account of time, and if you believe that causality only operates forwards in time, because then you don't have the value of a variable. And the value of the variable depends in time.
Okay.
And your social economic status
Okay.
today, for sure, depends on all kinds of things, and there are circles in the near past. But there's no direct causation of the values of things in the future, your social economic status tomorrow. It's not going to directly cause, I can't think of good examples, but whatever. Okay, but that's the idea. And so it doesn't, if you write down a model like this, you're not saying that the variables which these things stand for in the real world are caused directly only by their parents in the graph, but you're saying the real world is as if the probability distribution that you see is as if. Okay, and I should mention the name of a famous person in this field, a guy called Pearl, who's in computer science and artificial intelligence, and has written a splendid book called Causality, and it's already second edition, and people study it, and there's all kinds of stuff in there. I should also add here, I said medicine, but epidemiology. If you get medical data about a bunch of people and you want to know which factors are causing which diseases, that's you working. And so there are the sort of two slogans here. One is correlation is not causality. So two things can be statistically dependent on one another. Does not mean that one of them is the cause of the other. But there's another slogan which says no correlation without causality. That's called Reichenbach's principle. So it's a sort of philosophical principle that if things which vary randomly are statistically dependent on one another, so have a correlation, you can predict this one better when you know this one, then there must be the explanation of that is a cause. The explanation of that must be a cause. And so I can give you some little tiny graphs to illustrate it. So, I should say this one for a moment. So I'm going to look at something like a little graph with three vertices, and it says that this is directly caused by that, and this is directly caused by that, and the result will be that there's correlation between these two. So the path of arrows, the directed path from here to here, is going to be, according to the picture, will be explained by the intermediate variable. So the correlation between these two is caused by causality. But in this case, there's something else creating the causality, like this one. The third one is not directly caused by this one. So I don't know, kind of stupid examples. So you can hear.
Well, even if you switch that first arrow to
Again, yes. This is the most common, the one you most immediately think of. So here are a number of babies born in Hungarian villages in a year, and this is the number of storks which are nesting in that village. And there's an immense correlation between the two because the prosperity and size of the village is directly is sort of the cause, both of the many stalks which are there and the many babies which are being born. But you could also have priests and babies for the same reason per village, right? So there's correlation between these two, and it has a common cause. It has a common cause. When I had this, there's correlation between these two. It doesn't have a common cause, but it does have a causal reasoning behind it, why it is there. And I think we have to do now, yeah. And what happens here is that there's another one which people don't think about, which you don't have so much sort of instinct about, but which you should realize because it's very, very important. And it's a kind of converse. This graph is supposed to mean that these two things are independent of one another. They have got no common causes. And together they are the common cause of this one. Now suppose I look only at individuals for which this has a particular value. That is, those people who have a particular value of that are going to tend to have different values of these two than all people in general. And in fact, given this, there's going to be a correlation between these two. So, I don't know, this is lung cancer, this is smoking, this is another famous cause of lung cancer, maybe a genetic cause. And we might want to believe in advance that the genetic cause and smoking are independent of one another. If we pick somebody who doesn't have or doesn't get lung cancer, or does get lung cancer, and we find out that they don't smoke, then it's more likely that they do have a genetic disposition. So, conditional correlation can be caused by conditioning on effects. And we'll see that pretty soon. Okay, so by the time I give you a semi-formal definition, I can do that. I'll do it first over here for the undirected graphs, because it's more simple. And so what I want to say is what people assume, or what people mean by saying I have this graphical model for these random variables. They mean the following: that these are now going to be disjoint subsets of vertices in the set of all vertices, so you say different groups of variables. And then we can look at, then I'm going to write things like x subscript a for the bunch of variables with vertices in A. Think of this as a random vector, where we remember, it's not just a list of numbers, but it's a list of numbers which are associated to particular vertices, so we know which one is which.
So we could also write that as a product of E and A.
Yeah, it's a random vector taking values in this product space. And but if we count, we may have a few different A's and B's and C's for which the product space is R10 each time, but they are different R10s because they belong to different subsets of indices, and you need to kind of remember them. So I'm not quite sure what the good mathematical ways to say that.
Set theoretic.
Yeah.
That shouldn't be hard.
You could say it in set theoretic languages it's easy, and that's how I was taught it. And you guys are younger, so you all do things in categoric language, and I don't know what you're talking about. That's a bit, but anyway, okay. But then I hope you can understand what I'm going to mean. But for all A, B, S in V, such that S separates A from B. I hope, well, I can explain that with relative to this graph. X, A, the A variables are conditionally independent of the B variables given the S variables. So when you fix these variables, then these two become independent. So if there's a part of the graph over here, another part of the graph over here, and I cut out all interactions between an element of A. Okay, so here's A and over here is B. If if I condition on the values of the variables belonging to S, then there's no more path of interactions from A to B, and the A variables and the B variables are independent of one another, given the variables in between. Initially they were dependent, because at least if the graph is connected, then typically everything is dependent on everything else, statistically correlated. But, so that's very simple. And
Sorry, can I ask a question? Because
Yeah.
now I'm confused, because in your example that you've erased now,
yeah.
or am I confused because I'm
Yeah.
thinking of the A directed graph?
Yes, maybe probably, because
There, the middle point
yes,
does separate the two endpoints.
yes,
Okay, but that's
right, exactly.
okay.
Very
so-
good. Yes, you are anticipating the definition of
Okay.
directed acyclic graph models, which I will write out in all its appalling complexity, because you've got to face up to it sooner or later. S. Okay, so I'm now postponing the pain. S de-separates A from B. Okay, S, A, and B are disjoint. S can be empty, by the way. Then we are saying A is de-separated from B, but I haven't told you what de-separated means yet. The D is D of sort of direct into D, but it has a appalling definition. But anyway, this implies X, the same thing, XA is independent of XB given XS. So it's so you're conditioning on a bunch of variables, so you can stop causal influences from sort of propagating with the arrows. But the problem with conditional variables is you can create dependencies between not descendants but ancestors. So the definition of de-separation is a bit hairy. So I'm talking what I wrote so as not to make a mistake. And he says it's his definition, and I think it's the right definition, that you can, all these definitions can be posed in a positive and a negative way, and you can write down the definition of deconnected. I think he gives the definition of deconnected, so to get de-separated you have to take the logical negation of his conditions, and in the conditions there are both an and an or, so you have to get your mind around switching all of them and not getting lost.
So sorry, are these
Yeah.
statements
I haven't-
theorems?
Sorry?
Are these statements theorems or are they?
These are definitions, yes. Sorry, these are definitions of graphical models. So these are supposed to be definitions. I haven't finished the definition there yet because I haven't told you de-separated yet. But a graphical model for a collection, when you say what is a graphical model, you should say in advance what the spaces are and what the graph is, and then you say it's the class of all probability distributions of random variables x, v, v, and b, such that x a is independent of x b given xs whenever s separates a from b. So it's a class of probability distributions on this product space. So we can do a very separate, we can do some simple ones very fast over here because separation is obvious. So in particular here is a graph in which actually these two vertices are separated from these three vertices. But there are no other separations. Right? There's no other, except for the MTS, separating these three vertices from these two vertices. If you pick any number of vertices, like pick this one and this one, okay, erase these two from the graph. Well, these two are still separated from this one. There's basically only one separation in this graph, and that is the fact that the graph is not connected. As long as and so this graphical model says that these three random variables have any probability distribution you like, and these two have any probability distribution you like, and the three are independent of the two. Is that clear?
No, because what does it mean that you can have everything you like? Oh, but
It's
so
a
that,
complete graph, right?
Well, this subgraph is complete, and this subgraph is
so the
complete.
three of the triangle may be dependent.
The three of the triangle can have any joint probability distribution whatsoever on the space of the product of the three spaces, sets. And these two can have any joint probability distribution you like. Yes, dependent or independent as you like. The only thing we've fixed is where they live, where they take values. And this group of three is independent of this group of two. Yeah, it's very good to do some little examples. Now if I erase this edge here, okay, that's now a different graph, same variables, a different class of probability distributions. Because now, if I condition on this value, the set, sorry, not value, the set containing just this one single vertex does lots of separations. It separates this singleton from this singleton. It separates, but it also separates these from these, because there's no path from anywhere here to anywhere here, which doesn't go through there. There's no path at all. So you have to watch out with double negatives and things. But here, this model says something. It says that these two have completely arbitrary joint probability distribution, and I can tell you in advance now. It says that this one can have whatever distribution you like. Am I right? I may be wrong. Oh yeah, and these two are independent given this one, but they have whatever distributions you like of this one given this, and of this one given this. So you can build up the joint distribution of all of them by writing down the joint distribution of these two, a marginal distribution of this one, a conditional distribution of this given this, and a conditional distribution of this given this.
So these sort of extra things like the cherry on the left is independent of the stalk on the right, that will follow
Yeah.
from the sort of the two basic ones, that like the left-hand bunch, right? Because we had these sort of two basic things, that the left-hand bunch is independent of the right
Yes.
bunch, and the two cherries are independent of the top thing.
Okay, obviously two cherries, yes.
Oh, I mean, you could number them then. didn't you?
Yes, I could know.
Well,
So technically,
then there's another, I mean, you get other ones like one of the cherries on the left is independent of the
Yes.
whole thing on the right. But
Yes.
that should follow from the first two rules, I guess.
okay, now there is another issue, yes, indeed, of course, that a number, so I can write down all the conditional independencies which follow from the graph, which follow by applying this rule, and many of them will be superfluous, because many of them will be consequences of others of them. And we learned about that, I told you about that in chapter 4, that there were some For instance, there are some basic rules of conditional independence which are always true, and there's another one which is always true if there's a joint probability density which is positive, and otherwise a little bit tricky. And we also saw it was mentioned the fact that there is not a finite list of conditional independence axioms, and there are a finite list of axioms of separation in graphs. So you can, if I give you a bunch of random variables, it's sort of not possible to find a graph which, such that this rule reproduces all and only the conditional dependencies of the variables. There's a slight mismatch, which is embarrassing. But not in the case of a positive grade. Yeah. So yeah. So in particular, of course, Sutherland is interested in algebraic geometry, and so he's particularly interested in two special cases. One is the case of discrete random variables taking only finite many values, for which the conditional independence of two variables given a third is a polynomial equals 0, namely, in fact, a binomial. Yeah, binomial, two things of degree 2. So I should remind you again, won't. So he's interested in that case because these conditional independencies can be correspond to writing down a list of polynomials in the basic underlying probabilities which have to be 0. So it is an algebraic writing. The model thought of as a vector of probabilities, so that to each element of this product space there is a probability, and they're non-negative and they are to 1, and they have, and saying this says, and they live in a certain variety. Okay, and another case he likes very much is the case when we are told in advance that all these random variables together are multivariate normally distributed, in which case the joint probability distribution only depends on a mean vector and a covariance matrix. And it turns out that conditional independence relations are all connected to minus of the covariance matrix being 0. And I'll come back to it again in a little bit. And also can also be described in terms of the inverse of the elements of the inverse of the covariance matrix. So you can characterize the models in a nice algebraic geometric way in those two cases. Okay, now I have to tell you what d-separation means. Okay, so what does that mean? This is even earlier. C D separates A from B if and only if every path from A to B is closed. Oh, I'm going to have to define closed. Is closed by C. But first I'll tell you what every path is. Every path is a chain of vertices where with A at one end and B at the other end, and all the vertices are different in that path, including A and B themselves. The arrows can be either direction. So a path is not necessarily directed in this world.
Is C the same as S?
Yes, I should have said S. This is going to, okay. So every path from A to B has got to be somehow closed, remain closed also after you've conditioned. And the bandit is closed. Okay, path is closed. If and only if. Then we have to look at each step in the graph, in the path, and we can categorize them. So I'll do that here. We talk about chains, forks, and colliders. So a chain is a pattern like this. So you've got this path from A to B, and if there's a chain in the path, it means that there's one vertex in the path, and another vertex in the path, and another vertex in the path, connected like that. That's called a chain. Well, a fork, so a fork is obvious what it is. That's like that. You write them. And a collider is this. So it's a characteristic, I'm talking about the characteristic of the vertex relative to the path. Is in the path, the vertex in particular, sitting in a little bit like this, or in a little bit like this, or a little bit like this. So there can be all kinds of other arrows going in other directions outside. The path is closed, and it becomes, there exists a chain or a fork in C, in S. I should say on the path, but with the central node in S. So the path is blocked by blocking S. But we also want the path not to be opened by blocking S. So this is where we have an and. So here's an or, here's an and here's a no collider on the path. On S or with ancestor in S. Sure. And what this is, the intuition is, forget about this one for a moment. So we're asking the question, are A and B correlated with one another, or statistically dependent on one another when I condition on some variables, certain other variables. Now, if there's a particular path, which, like every path in principle allows some correlation to exist, but if the path contains a chain and we condition on the element of the chain, then we block the dependence from passing through that element. And also the fork, if we condition on this, then these things become independent, and there's no way that saying things about this can influence things about that. Except if there's something like this in the path, and it's not this variable which we block, but we block, no collide on it. Yeah, if we block this, then we block dependence from spreading. But also if there's, if this thing has an ancestor in S, by conditioning on this one, we actually create statistical dependence between these ones. That's the intuition.
So when you said, like, if the collider itself is an S, the same thing is true, right?
Yeah.
Like if you condition on
It
the
creates,
collider,
and it can create dependence. Or it does in general create dependence between the two parents of the collider. But of course, the propagation of dependence might be blocked by other things you condition on.
so if you have a collider, but then you have a collider in S, but then you have forks in S either side of it, that would seem like it would be okay, but apparently it's not allowed.
You can't, no. No, if I have got the definition right. I think I got it right. I thought I had it right yesterday and the day before. Okay. Well, so this may not be exactly right, but I think Sutherland's definition is exactly right. And anyway, I hope the intuition is clear that you can stop dependence from propagating by conditioning on nodes like this, but you can create new dependence when previously there wasn't by conditioning on nodes like this, or even on conditioning on an ancestor of this.
So can I ask for
Yes.
a specific example I have in my head now? What if I have 2 points that
Yeah.
are without an edge,
Yeah.
and so S is empty, and A is the one point, and B is the other point?
Yes. Now these should be
Then there is no chain or force.
no.
So So
there,
no-
there are no paths from A to B, so there's nothing to verify.
oh, that's also true.
There are no paths from A to B, so I think
Yeah.
that lets us off worrying about what
Okay, fair enough.
Yeah, yeah, that's good. Yes. So, so if this graph falls apart in 2 parts which are with no edges between them at all, then everything on the left together is independent of everything on the right. So that's nice. Okay. Okay. Now I always break my head about worrying about whether I said it right or wrong. Unfortunately, there is an equivalent condition which is, for me, much more attractive. But the thing is that this one is, there is intuition with this, and people get good intuition about this one, and they can look at the graph and they can immediately see, and this is nice for people who are using these graphs, who are sociologists or economists or whatever, and maybe not so strong mathematicians, but they can understand how to look at the graphs and see what it is saying. For us mathematicians, or for me anyway, I like the following equivalent characterization. S separates A from B, if and only if, so all that, if and only if S separates A from B in a particular manipulated subgraph. Namely, we're talking about A and B and S, so we restrict the graph to the union of A, B and S. So we look at these vertices and we look at the edges between those vertices only. And then sorry, that's not quite right. We look at these vertices and then we look at what is called the ancestral subgraph of the original graph. That's all these vertices together with all the vertices which are ancestors of vertices in here. And so we sort of, we add to these vertices everything where there is a directed path going to these vertices, everything from which there is a directed. So the terminology is very sort of genetic or biological. Here's a particular vertex. These two are called its parents, and this is called its child. And A is a parent of B if only if B is a child of A. Moreover, this is an ancestor of this. And this one is a descendant of this. And A is an ancestor of B if only if B is a descendant of A. And with that, not quite sure if it's common to say that A is an ancestor. Are you your own ancestor? Are you one of your own ancestors?
Yeah, surely.
It doesn't sound right, but it could be. And are your parents also your ancestors? They are,
I think so.
of course. Even if they're still alive. Yeah. Okay, but what was I doing? I haven't quite finished yet. So now I've just restricted attention to part of the graph, the only part of the graph that's relevant. You can argue that we only need to look in this part of the graph, but then we have to do one operation to it, and that's called moralization. Smile. What does moralization mean? It means you marry the unmarried parents and you drop the direction of the arrows. So you keep the edges, but you forget their direction. So if I want to moralize this graph, I have to marry these two people here who are parent of this child. So we have to add this edge. So, well, no, and this one, and this one. No, maybe.
Parents of.
Sorry, these. Yeah. Which one? Did I give this one an arrow or
Yeah.
is it there? If this is an arrow, if this is part of the graph,
Yeah.
then these two are children of this one. So these have to be joined. These two have to be joined. And then we erase the